In this work, we present an open-sourced end-to-end interactive design interface, which aims to enhance the efficiency and accessibility of resistive tactile sensing design. Human sense of touch encodes and conveys a vast amount of information about how we engage with the physical world. Tactile sensing is a technology that captures such sensation. Tactile sensors hold significant value across diverse applications, such as human-computer interaction, healthcare, robotics, and education. As tactile sensing interfaces must be designed in diverse shapes, sizes, sensor layouts, and configurations to suit specific applications, developing these highly customized interfaces is often time-intensive and requires advanced expertise in hardware and software, posing significant barriers for non-experts such as hobbyists or researchers from other disciplines. Resistive sensing converts pressure into electrical signals by measuring resistance changes in an array with electrodes on both sides of a resistive layer. Appropriate wire layout should be designed based on the required sensing area and connected to a connector for signal output. To develop an accessible design interface for resistive tactile sensing, we first conducted a formative exploration of the motivations and design considerations from participants with varying knowledge backgrounds. Drawing on the insights from this study, we developed a web-based tactile sensing design toolkit. Starting from the formative study, we conducted a semi-structured interview user study targeting both experts in tactile sensing design and non-experts with no direct experience in this field. Participants were asked to rank the difficulty and boredom for each given working pipeline and think aloud while solving two hypothetical tasks about resistive tactile sensing. We found out that experts seek tools to reduce repetitive manual work of wiring overlay and to comprehensively consider all requirements when confirming parameters, while non-experts lack knowledge of parameter settings and wiring methods. We then defined two design principles for the tactile sensing toolkit. First, to offer standardized workflows and ready-to-use templates for efficiency. Second, to support customizable parameters and dynamic layouts that can be adjusted to fit specific project needs. Based on the quantitative and qualitative analysis, we designed the interface toward ubiquitous tactile sensing. We identified three key stages for parameter input and user flow as follows. Shape and outline. Define the shape and dimensions of the interaction area. Sensor layout. Specify wire number and thickness, select appropriate wiring density, and determine minimum spacing between wires and connector size. Validation. Avoid wire crossings and ensure sufficient spacing between wires for safety. Additionally, provide warnings for wire intersections that fall outside the sensor area. We translated the identified stages into core functional modules integrated into the toolkit's UI design as follows. 1. Asset management. 2. Automated sensor layout generation algorithms. And 3. Prompting and export. Users can import an SVG image or draw shapes on the canvas to convert them into sensor areas. A sampling algorithm is applied to approximate curved shapes as polygons. By inputting appropriate parameters, such as the number of wires along the X and Y axes, a wire layout is automatically generated. To meet diverse user needs, we provide two types of grids. The regular grid generation method creates a uniform grid within the bounding box of the target shape, intersecting the grid lines with the shape's boundaries to form a precise grid. The shape-adapting grid method uses a shape-scanning algorithm to evenly distribute wires across the sensor area. Users define entry and exit points, and the algorithm adjusts wire orientation and spacing based on the shape, with wires connecting across scan segments until the exit point is reached. Additional entry-exit pairs allow for multiple directions. When users perform connection operations, the system automatically identifies intersection points along the sensor area's contours and detects available connectors. It then optimizes the connection order to minimize intersections and generates the corresponding connection lines. If the parameters are unreasonable, such as excessive density or intersecting wires, the toolkit will prompt an error for easy modification. We also provide various common templates, such as basic shapes, human body parts, robot arms, etc. In asset management, users can control the relationships between the shape, sensor area, and connector layers, and finally export the layout by layers. Future work will focus on extending its capabilities to 3D designs and evaluating its impact on fabrication performance and user experience. Thank you.